Okay, we're going to use example number 9 to show that this integral of e to the negative x squared dx from 0 to infinity is convergent. Now we can't evaluate the integral directly because the antiderivative of e to the negative x squared is not an elementary function. So we're going to write it in two different forms. We're going from 0 to infinity e to the negative x squared dx, which is equal to 0 to 1 of e to the negative x squared dx plus 1 to infinity e to the negative x squared dx. And then observe that this first integral, okay, here on the right hand side is just an ordinary definite integral. In the second integral here, we use the fact that for x is greater than or equal to 1, we have x squared, which is greater than or equal to x. So therefore, multiplying both sides by a negative, flipping the inequality, makes negative x squared less than or equal to negative x. And therefore, we could say that e to the negative x squared is less than or equal to e to the negative x. Now the integral of e to the negative x is easy to evaluate. So if we evaluate that integral, we get the limit as t approaches infinity from 1 to t e to the negative x dx, which is equal to the limit as t approaches infinity of e to the negative 1 minus e to the negative t, which equals e to the negative 1. Thus, taking the function f of x equal to e to the negative x like we did up here, and g of x, which is equal to e to the negative x squared, in the comparison theorem, we see that this integral e to the negative x squared dx is convergent. And it would follow that this integral going from 0 to infinity is convergent. If you take a look at table number 1, if you look at t, the values of t, when you plug in 1, when you plug in 2, when you plug in 3, 4, 5, and 6, you can see that eventually it's becoming a value of 0.88. So it's consistent as it is increasing.